Nanis. I'm with Andrew Sue over at the Scripps Research Institute. And I'm actually pretty excited to kind of cover this talk because I feel like it will hopefully be a slightly different topic than what, or the type of work that most bioinformatics do in their day-to-day. And so, marked here, a structured heaps on brick and mortar, and I'll attempt to explain where that comes from. So, back in 1665, the Philosophical Transactions of the Royal Society, as far as I know, has kind of been perceived as what would be considered the first academic journal that was published. So that was 350 years ago. Jump ahead, in the late or mid 1880s, about 135 years ago, Nature and Science had really gotten kicked off with what's considered contemporary academic publishing, and not much has changed. But what I want to specifically point out about at least Nature is their mission statement. So the first part of their mission statement has always been, or most recently has been revised specifically to make clearer, is that one, their main goal is to serve scientists through prompt publication of scientific advances in any branch of science, in addition to providing a forum for the reporting, discussion of news and issues concerning that science. Secondary, their other core part of the mission statement is to ensure results of science are rapidly disseminated to the public throughout the world in a fashion that conveys their significance for knowledge, culture, and daily life. So they serve not only for scientists, but for the public to be able to get the benefits of the research that has been done. If we jump ahead to a Nature paper from fairly recently, we can see that they moved to a PDF, and so the PDF format was released in 1993. It has since gone, I think, like 6 major revisions, with the last one being the ISO-compliant modification in January of 2008. Allows PostScript, font embedding, so that fonts can be packaged, storage system to embed images, layout, graphics, and all of that. Another big technological advance Nature did was in 1996, they made a website, so they were able to put these PDFs on the internet. And in 2005, they made a podcast, which is great. One of the more recent things that Nature has also done is to kind of start a big initiative to get richer and more engaging supplements for papers. And so this is great. Being able to kind of go through and reproduce, theoretically, some of at least the computer science-based or pragmatic parts of a paper is very, very useful. However, even IPython notebooks, which is what's shown here, don't really solve an issue of being able to understand what's in that paper. So efforts like increasing the media richness of the supplements allows potentially higher reproducibility, but that doesn't necessarily equate to the dissemination of the knowledge that's contained within the PDF. So I wanted to show this sculpture by Noor Ali Kalagani, which is, I think, a very beautiful representation of the state of academic publishing right now. And that's because the PDF is just as much as a brick as a journal article was back in the 1880s. It's very difficult to be able to extract the knowledge that's contained within that document. And what's beautiful about this sculpture is that the bricks that are in it are of different ages. And so you can see that, a PDF from last year is able to live along a PDF of a scanned version of the, Watson and Crick paper or whatever. They can exist together. And this brick and mortar structure provides a core support structure for the academic publishing world. But what's also really beautiful about this analogy is that a brick wall allows ivy to grow off of. It allows a lot of new kind of life form and branches to take form based off that, because the PDF and the paper isn't going anywhere, right? And so I think what's really important to this story is this philosopher who put out a book in 1964, Marshall Mcluhan. And so this is the book. It's Understanding Media, the Extension of Man. If you're unfamiliar with Mcluhan, he also predicted the World Wide Web like decades before it came out. But what's relevant about this story is that he proposes that modern media are extensions of human senses and that the content of any medium is always that of another medium. So the light bulb is the extension of daylight, writing is an extension of speech, print is that of writing, and then the print itself is the extension of the telegraph. And I wanted to bring this up, this idea that the medium embeds itself in the message, creating a symbiotic relationship by which the medium influences how the message is perceived. So the medium is the message, is kind of what he's been really known to bring forth. And I think this is relevant because the scientific message of today is largely the same as it was 100 years ago, right? The presentation of reproducible experiments, the scientific method through verbal articulation. Granted, it's been further refined into sections and all of that, but it's been largely unchanged. And kind of what I want to talk about throughout through this little presentation is that I would argue that the perceivable understanding of the message that's contained within this PDFs can be a lot better. And so I don't think that the way that we understand paper findings is necessarily where it can be or where it should be. And so kind of the whole goal of Mark to Cure, which is what this is about, is to kind of revisit the academic publishing model and to think about how you assemble a network of biomedical knowledge that is comprehensible, current, computable, and traceable. And anybody that uses PubMed would know that this is really a very important time to do it. The amount of papers that get published on PubMed yearly grows in an astronomical rate. If you do the math on this, so this is the number of new PubMed publications over time since the early 80s. So if you do the math on 2014, we get a new PubMed article about every 26.5 seconds. And so like, it doesn't matter how much of an expert you are in your niche or your domain, it's impossible to keep up with the literature. Going back to the 60s for a second too, back then this thing called a mesh term was kind of invented. And that's, a mesh term is roughly defined as like a comprehensible controlled vocabulary for the purpose of indexing journal articles in the life sciences. It's used by Medline, PubMed, Article Database, National Library of Medicine, clinicaltrials.gov, which has other problems, but it uses these terms. But mesh terms in themselves are very hard to query and compute. You can see I put an example at the top here that does a PubMed search for a neoplasm containing text, or pardon me, not text itself, but an article that has neoplasm associated mesh term, or the article itself contains the letter CANCER. And so from a knowledge standpoint, that is like a very rudimentary search. It's a string search. It doesn't tell you that much about the article. If we look at what's underneath it, it's really hard to tell, but that search is for any PubMed articles that contain a tyrosine kinase inhibitor and a hematologic cancer. And so what does that search mean? It could mean any of those types of tyrosine kinase inhibitors, any of those types of cancers, and the resultant articles that come out of that could be any permutation of those two combinations. And so being able to search through PubMed and query this, and even use a computer to understand some of these papers, is next to impossible. It's really hard. To try to tackle this problem, there are like two main tasks. There are actually more, but I'll simplify it for now and just say these are the two that we're concerned with. We need to be able to identify the biomedical concepts that are actually contained within a paper, in addition to identifying relationships between those concepts in a paper. And if you can do that, you should actually be able to do a far more richer search. And so we'll start to break these down. The first one is how do we identify biomedical concepts within a paper? I said I'd simplify it a little bit, but this is actually two steps. The first of which is entity recognition. So just extracting strings out of an abstract or title to say that is some entity. The other step of that is to say that entity is associated with some concept in ontology, but we can get to that later if we want. So how do we do this? How do we identify these concepts in a paper? we can throw a lot of money at it, and it will eventually get fixed, right? But that's not necessarily a great way to do it. I think we did the math, and it'd be like $2 or $3 million if we hired full staff of people to be able to do this on the fly. It's not feasible or not realistic. The other kind of approach is that we can pay people on the internet to do this. So this is Cindy. Cindy is what's referred to as a mechanical Turker. She is kind of the true definition of a 1099 worker in the contemporary economy. She's a freelancer that works on the internet for ephemeral tasks. I don't know if she worked on our task specifically, but people like Cindy did basically the entity recognition task that I just kind of explained, that we could throw money at and solve. The benefit of people like Cindy is that you can train them really fast. They stay up all night and work really hard, and you don't get that from somebody that sits in a cubicle for 8 hours a day and takes a 1 hour lunch break and has all these other things associated with their life. And we can train him or her to do our entity recognition task pretty well. If we take a group of Cindy's, these mechanical Turkers, to be able to kind of extract entity terms out of a paper, we can try to quantify their performance using precision, recall, and the harmonic mean, which is the F-score. And so what this shows is as we get more Cindy's, or as we have more people actually work on a single document and start to annotate it, the precision will go way up, because you would be able to imagine that if you have 15 people looking at a document, the one or like the handful of terms that they all select are probably pretty good, right? However, you then have the inverse problem where as you introduce a higher K, the probability that they're going to have a greater recall is like way higher, because you might get somebody in there that doesn't really understand it and just selects a word at random, and that's a false positive, and we don't want that. So if we look at the F-score, we can see that like a very good combination of the balance between how many people we need to do a document to a sufficient rate is right around like 6 mechanical Turkers. And so this was a study we did, I think, about a year ago, where we found like 6 is the sweet spot. But it's also worth thinking about, we can't just pay 6 people to do a document. We want to pay more, and then from the more people that we paid, select which ones are probably the best at answering it. And so we also looked at how many workers does it take to basically saturate our performance maxima on a document. And so this shows that as we approach like 15 or 20 workers, the theoretical highest potential for the F-score to come out of it starts to plateau. And so we really at most need 15 people to do a document. After that, it isn't really worth paying more. And so we need to think about, how do these numbers compare to how other people have done this in the past? And the 2 graphs that I just shown, we were able to compute those F-scores because somebody prior to us had created a corpus of around 700 documents where they had paid around 12 annotators plus 2 administrators to do this for an unknown amount of time with a non-disclosed amount of money that was spent on it. So those are 2 variables that we don't know. They are probably pretty high. But we know that if we have PhD professional people annotate these documents, their F-score is around 0.87, which is very respectable. If we compare one of those PhDs to a Cindy, they do 0.78, which is not as good, but it's not horrible. In addition, we know for a fact that it might take a mechanical Turker, 3 to 6 days to do one of these data sets, and $40, right? Because they get paid 6 cents an abstract, and times 600, you times 40 times 15. If we go up to our consensus for the maximum number of people per document, that's like 600. There's some buffer in there because we got to train them. Some of them drop out, things like that. But we can basically annotate around 700 documents at a sufficiently well, I think a very well level, for around $600. However, this is nice, but again, if we were to scale this up to a new document every 30 seconds, that is millions of dollars a year. And so is there potential to get that number to 0? And the way that you would try to answer that question is, can this be crowdsourced in some way? And this is how I kind of wanted to approach and introduce Mark2Cure, because that is what Mark2Cure is. It's a crowdsourced approach to try to be able to get these entity recognition terms in addition to other tasks associated with understanding knowledge in a document via citizen scientists on the internet. And so we also ran another experiment with the same around 700 documents. We got an F-score around 0.84. We think that's within the standard error, so it's probably noise. Training might be able to improve that, but it's on par. It was done in about a month, and aside from myself and other members in the STU lab, it didn't cost us any money.
So I'm wondering what Cindy's error rate is over time. I imagine earlier in the process she would do better, and eventually she'd get bored and start caring more about piecework income?
It depends. So it depends heavily on the training that they were exposed to. In addition, if you train a mechanical Turker, their performance will go up after like 20 documents, they plateau. But then what can happen is if they see a new scenario in the literature that they thought they were trained on, but they don't actually have a full understanding of that like concept, their performance will drop off because they don't have any feedback to tell them that you're doing it wrong. And so that is like a very difficult problem that I skimmed over. Yeah, it's very difficult to monitor the performance, but it does fluctuate greatly based on their training. Yeah.
Are you going to have some examples of the kind of entities that, you know, the degree of sophistication that you're looking to pull out?
Yep. Yeah. Absolutely.
Okay. Cool.
So the crowdsourced approach to do all of this is Mark2Cure. Mark2Cure is a site online right now. Anybody can sign up. They go through these training tutorials they put together to instruct people how to do this work. And the main goal, again, of Mark2Cure is to convert free text into structured data. And so if we compare Mark2Cure to other crowdsourced applications that are out there right now, for those of you who are familiar, Universe is a way to do really cool things looking at the satellite imagery. They have around 1 million volunteers folded. From the Baker Lab, obviously does all protein folding simulations. Around 300,000 volunteers. iWire is another about half that, and then RNA one is around 37,000 again. So that's a significant number of volunteers. And one of the first questions we needed to ask ourselves was, given the publication rate of new articles on PubMed, is it even feasible to have the number of volunteers to do all of this? So this is some napkin math that computes to about what we think it would take for the number of volunteers to be able to take that fire hose pipeline of all the new articles. And we would need about 16,000 volunteers, which if we go back here, is around like half of our lowest competitor. So we feel like this is a realistic goal that we can set for ourselves, and it's not some pipe dream. I wanted to show you the actual task that people do themselves. So a user will log into Mark2Cure, and they're presented with the title of a paper and the abstract. We don't tell them the PMID, because then they could go up and maybe try to look at other answers on it or something. So we let them do like a rudimentary search for the terms that I highlight. I wrote a JavaScript library to allow like a very rapid text selection interface so that you can't select like the letters in between a word and then it messes up the whole span selection. That is a huge problem. You can see that we have 3 different concept types, so disease concepts, gene concepts, treatment concepts indicated by different colors. And so if you click on a term 1, 2, or 3 times, kind of like in Minesweeper, it will switch type. And so they can like very rapidly go through here and start to highlight a word. Here's a treatment, another treatment, and I'll wait till this player actually submits this document so we can see what happens when they submit it. So this player was actually me, and what I just did is I just clicked next or submit document to submit my annotations. Once you submit a document, it's kind of like a ratchet. You can't ever go back because we don't want to show somebody the answers that somebody else has put in and then they modify it. You know, that's not a system. That permeability of like knowledge is not what we want. We want a user's intuition. I don't think there are any cases on here where the type disagreed, but when we compute the F-score, so that's actually like a 0.78, that's done by comparing the spans that were overlapped and the types of them. And the user that we compare you to is not random. So in this case, Gattaca Yeah, well, that's Ginger. She's very good. Like every night at midnight, we compute the most up-to-date F-score of all of our users, not only on a site-wide basis, but on a group basis, which is kind of like a quest-level organization of how we compartmentalize docs on here, so that I know for a fact that Gattaca is the best person to compare myself to when doing this game. And this way, the reinforcement that we get from other players is as strong as possible.
Have you incorporated AI into this at all? Because most of the terms that you have listed here can easily be.
I'll get to that.
Okay.
So you can imagine we've been doing this for a couple months now, and one of the results of all of this is, okay, so this is again just the home page. This is a organization of other documents. But we're able to look at the network now of what people have highlighted. So this is a case where we've had people do a group of documents. We know basically the terms that they've selected in it, and we know the terms that other people, all of our users have selected. So we show a network where the nodes are the actual recognized entities. They're different types, so we see like diabetes in there, P53, obviously, like all these other things in there that are treatment, genes, or diseases. And the edges are the PMIDs that connect those entities, so the documents that do that. In this particular network, we set a threshold of there needs to be at least a consensus of 15 people that have connected a PMID with 2 terms to be able to do this, or else it would just be huge. But this allows us to have kind of an overview understanding of the relationship between all of the concepts within a paper dynamically on the fly.
When you say 15 people, do you mean 15 papers and 15 people, or 15 people in one paper?
15 individuals. I froze them. Well, maybe I didn't. 15 people said that these 2 terms were connected in the same PMID. Yeah. Okay, so to get back to the title, we've got into a point now. Oh, let's all back up. This is Robert Smithson sculpture from the 60s, and he was a land artist that challenged a lot of the entropy in the natural world and how it's organized. And I think this is a really beautiful analogy for the knowledge that we've started to collect, because we've started with these 700 papers that we knew the answers to, right? Because somebody else paid a lot of money to get those answers. And from that, we trained our new users on this existing foundation of pre-existing knowledge. From that, as you pour sand on the top of this heap, it will disseminate out and start to get towards increasing the breadth. And so once you're trained, you can imagine those grains of sand approach the edge, and so our experienced users really push the fringe or push the boundaries of human knowledge that's contained within these documents. So that is our organized heap of data that has kind of come out of this effort. Going back to the 2 problems of this challenge of understanding what's in a document is, once we've identified these concepts that are contained within there, it's really useful to know the relationship that they have in it. So if a treatment type and a certain cohort or a certain phenotype appear in there, is that treatment good or bad, right? Are there negations on it? There are so many different types of relationships that we can define for concepts that we want to have an understanding of. Now, I would be lying if I said we were the first people to even approach relationships when papers were not. This is a great example of a way to visualize some relationship annotations within an article. I wanted to present this, though, because as much information as is contained within this UI, if you present this to a Cindy or to someone on the internet without much experience, it is not fun. No annotator will look at this and say, oh, I have a blast doing this. I want to do this for free. And so one of our challenges is, how do we take this interface and turn this into a task that we can kind of make really rapid and really accessible to a lot of users? One way we do that is we take an ontology of relationships, or we kind of curate our own relationship structure that we can have for our terms. This is just a snapshot of one of our structured JSON files that defines the relationships, where we have genes and diseases, genes and chemicals, chemicals and diseases. Also the expression of mutation is associated with post-translational modification. So we can define all of these pre-existing relationships that a user can select from. And even with us doing the manual curation to make these relationships saves the user a lot of time. So the way that this is kind of manifested from a UI perspective, kind of similar to the previous screen that I had just shown, is rather than being able to select on any of these words, you just want to be able to select, is it related to or has it no relation to? However, one of the distinction about this type of task, which is kind of difficult to grasp sometimes for a lot of users, is that relationship can't be based off anything off the internet. That relationship needs to be based off what's in the text, right? Because regardless of whether or not that relationship is true, it needs to be based off what information was presented to you. And to show this kind of in action, or why we took this approach in terms of kind of caring about user speed and effort, is that now a user can enter the game, or enter the initiative or the Marketeer, and like burn through some of these relationship types, right? You'd imagine you read this article once, you start to have like a good understanding of everything that's in it, and then you can say yes, no, not related to, that's not actually a gene, let's mark that off, and get through these really quick, which you can't do in some of the other interfaces. So that is the relation kind of aspect of this problem. Not promoting Earth Day, but going back to this AI question is, at this point we've collected a lot of data, and we have this data, but now what? What do we do with it? And so, as we all should, we should make this data accessible. For one, we should let other people know about it. And by letting other people know about it, we hope that they can then use it to make their tools better, right? And we want their tools to get better because we can imagine using their tools to automate human contribution. So theoretically, as their tools get better, we can have our human contributors start to do more difficult tasks or more specific tasks that previously might have been automated, or the work that they'd done previously would have been automated, or couldn't have been automated. It can be now, so they should do other work, right? And so everybody in this like recycled model of knowledge, everybody should move forward in parallel. So in order to make this accessible, we have a BioC endpoint. BioC is a natural language processing file format XML standard. So in real time, we have an updated API for all of our annotations that come out of our system. So that approaches step one. Step two is kind of how do we take some of the AI and make that, or use that technology to make our users' life easier. And so you may have actually caught, when I was demoing, or showed the demo on the entity recognition UI, there were some terms that were already selected. Those terms aren't based off a previous user, or like maybe this user came in and quit and then came back 20 minutes later. Those annotations that were shown in there were computed or basically pre-populated from Pubtator. And this idea is that because we have this API now, we can give all of our results back to Pubtator. They can train TMChem, denorm, any of their machine learning algorithms. We pull those in real time, and then we use that to pre-populate, again, the UI. So somebody might be able to do the same document maybe 1 year later, and the terms that are pre-populated can theoretically be different, right? So that they can continue to refine and improve these machine learning algorithms. So the machines and the humans don't have to go head on head. They can work in parallel, which is good. I wanted to kind of end this presentation with this last slide, which is, I think, really important. And I didn't cover any of this for the sake of time. But we've taken the approach with Marketeer to focus on rare disease groups, cases where it doesn't matter how much money you throw at a disease, it doesn't matter how many 5Ks you run to try to earn money for this disease. The only thing that this disease needs right now is people to read these papers, people to focus and spend time annotating articles that might be related to a rare disease that just doesn't have the following of like breast cancer, for example. And so we ask people, why do they contribute to our initiative, Mark to Cure? We've had users in here for months and months who are extremely active. And I think when you think about what is their initiative and what is their goal, and why do they contribute to us, and do they share the same kind of big pictures, ideas behind Mark to Cure as us, the answer is always yes. And I think some of these kind of quotes do a good job of explaining why people, in addition to just our own academic interest in this, feel a need to be able to contribute. Because these may be people that don't have money, that can't help in any other way. And so that shouldn't be perceived as wasted effort. We should perceive or think about new ways to be able to engage them. And that's what market cure does. So that's it. Yeah.